Everybody, it is office hours. Good to see you here. Kayla, what are we working on today? Mubot is waking up. Good to see you, Bailey. Try again. Mubot just woke up. Let's throw out some extra points there. I think Kayla just typed points. Mubot is awake. Mubot is awake. Let's give out 100 points here. Mubot, there we go. Mubot's talking some points now. I don't know why he's slow sometimes. I don't know why. And I'm using the old streaming service. So maybe I should maybe keep trying the new one, the new OBS. But the background's working here right now. I do not understand things. I don't know why the world works sometimes and why it doesn't. Can we do chapter 14? A sample is chosen randomly from a population that can be described by a normal model. Complete parts A through B. Watch, I see it before people even post it. For some reason, Mubot's in the future. I think YouTube has like a filter, and Mubot sees around like the filter. I think there's like a, which don't worry, it's like YouTube is just like, I don't know. It's weird. Mubot sees things before I see things these days. I can watch Mubot's stream, and maybe I don't know how he does it. I don't know how he exists in the future, but he does. Mubot is outside of space and time. Mubot. We're pulling up chapter 14 right here. So Bailey, we'll take a look at this. Great question, Bailey. Let's see, chapter 14. Okay, sampling distribution. And is this the homework or the quiz? Chapter 14, a sample is randomly chosen from a population that describes. Is this homework or quiz, Bailey? Describe the shape, center, and spread. It might be quiz. Let me do chapter 14 quiz. Chapter 14 quiz. I hit preview. Can we only do preview on this one? Stop doing that. Ads pop up. Replace questions. There we go. Let's see. Sampling distribution. Here, we'll hop over to the main screen. Let's do this. Let's see. You bet. I'm struggling with the interpretation of the partial F test in layman's terms. I have the code and basic understanding. You bet, Kayla. We can definitely do that. Thank you, everyone. Let's do this question here, and then we'll do some 320 interpretation. Which one is it? Is it showing just a blank screen? I'm sorry. What is this I think this is the one right here. I think it's the one that Bailey wanted right here. I'm not having those issues today. Samantha, have you tried I know it's like the most common thing to ask. One, try resetting your computer, or try a different browser, like try Chrome or Firefox. Sometimes there's just intermittent issues for different browsers or different pop-ups. So as soon as you have issues, let me know. Yeah, and it's weird. So Samantha, keep us updated. And I've got a My Pearson rep. If the problems persist, we have someone we can reach out to. So please let us know. Try switching browsers. That'll usually fix the problem. But so far, as of this week, we did have that 1 week, last week, when everything was crazy. Last week, there was definitely problems. This week, I haven't really seen anything, but sometimes just there's intermittent problems. So keep us updated. Yeah, keep us updated, Samantha. Thank you so much. Let's throw some 50 points out here. Good to see you here, Leslie and Samantha. Good to see everybody. And I mean that. I love it when people are here for office hours. Makes my day. I think Chrome works best. You see, I use Chrome. Chrome usually works the best. It can be like a pop-ups issue. So you can get all browsers to generally work with My Pearson, but sometimes it's like you have to like enable all these different pop-ups and stuff because the browsers are like, what is this site trying to load? It's trying to load homework problems. So when we talk about the sampling distribution for the sample mean, well, what is the point of the central limit theorem? The central limit theorem is going to say, that's not the central limit theorem. The central limit theorem is going to say that the distribution will become water and water. Like if we have a distribution that looks something like this right here, as we take larger and larger samples from it, like of n equals to 10, and then we get to n equals 25, what is the distribution going to start to become? And maybe we get to n equals 100, where we take 100 observations. The distribution, I guess technically, to make this visually, really, there we go. To make it more visually accurate, it would start to look like this. Sure, that's good enough. So the distribution is going to become water and water. Two things, and I guess I drew that one decently enough, but it's going to become water and water as the sample sizes get larger and larger. Two things happen as we go from the original parent population, which would be individual observations, to where we take so many observations here, and then we take the mean of these, like 100 observations, and we take the mean of those 100, the new distribution of the sample mean will become water and water according to the central limit theorem. So this answers the first part of it. The shape of it's going to be what? The shape of it's going to look a lot more what? Because that one's really super skewed up there. So that one up top is really crazily skewed. And by the time you get down here, it will get tighter. That is true, Bailey. And we're going to see that here in a second. And the shape of it, so it is getting tighter. That is very, very true. And it's also going to look, instead of skewed, it's going to look way more normal. Great job, Leslie. So the central limit theorem states that it's going to start to look more normal. So, well, we didn't really narrow down the options, did we? But the center of the distribution, we can do this mathematically here. The center of the distribution is going to be described. Let's use space pen. We haven't used space pen forever. The mean of the distribution of the sample mean is equal to the mean. The standard deviation for the distribution of the sample mean is equal to the original standard deviation over the square root of n. So these are just the formulas we're going to use right here. The mean for the distribution of the sample mean is equal to the mean. The standard deviation of the sampling distribution is equal to sigma over square root of n. So that's the standard deviation. That's the mean. And let's look right here. So the center of the distribution will be equal to mu, and the standard deviation will be sigma over the square root of n. And that's exactly what we're writing up here at the very top of this. We're writing this right here, that the mean for the distribution of the sample mean is equal to the mean. The standard deviation for the distribution of the sample mean is equal to sigma over the square root of n. And that's what it says right here. The center, which is the mean, is equal to the mean. And the standard deviation, which is the variation, is equal to sigma over the square root of n. If a larger sample is chosen, what's the effect? So now we need to look at where n is impacting it. So where is n impacting this? What is the only thing that's going to change for larger samples right here? You can just type 2 letters, or you can just type 1. So what is the only thing that's going to change for larger samples? As we get larger and larger samples, what will change about the sampling? And you can see it right there. You can, like, if we were to keep drawing this, and we were to draw what happens, you would see something like this, and then the sample size would get larger, and the sample size would get larger, and the sample size would get larger. I guess I'm just such a bad artist. So you can see, hopefully, in sample size would get even larger. You can see what's happening to it with Brian's horrible drawings. Horrible drawings with Brian, because he's not an artist. So what happens to it, just looking at it formulaically, without the ability to draw? Formulaically, this and this and this is getting smaller as the sample size is increasing. The formula denotes to us that the what will get smaller. As the sample size increases and increases and increases and increases and increases, the standard deviation will get smaller. So the standard deviation will be smaller, but the center remains the same because the center is just mu. So mu is not impacted by sample size, which is n. So we should get that right. Yes, I'm always worried we're going to get one wrong, and I'll be like, what? What's going on? So that's got it. Does this make sense here, Bailey? This is basically a review of the equations. Really good conceptual one right here to understand and to be able to then write out and kind of explain what is going on with these equations. So although, once you know the answers to this one, it's not so bad, it goes with these concepts right here about the mean for the distribution of the sample mean and the standard deviation for the distribution of the sample mean, how the distribution will become more normal, which is the large enough n, nearly normal condition right here, and then we can see the standard deviation getting smaller. Yeah, Bailey, great job. Hey, Bailey, I don't care. We're going crazy on points today. It's Wacky Wednesdays. We don't see Crash nearly enough. Wacky Wednesdays. Give out some points. Just going crazy. It's end of semester. Not end of semester yet. Let's go ahead and look at some code. Some code right here. We got big code on the screen. So looking at some code right here, this is Kayla's question. Let me do a cut in the video. So now we're going to talk about, this really helps me when I'm putting in the timestamps layers. It helps so much. Got to keep remembering to do these cuts in the videos. So now we're going to talk about some 320 for a moment here. We're going to talk about the partial F versus just how to interpret it and what it means. So let's go talk about some partial F right here on the main screen. Okay, so with talking about the partial F, we need 2 models. I really think, hopefully this visualization starts to make sense. Let's visualize again what the partial F does. So when we do an F test, like, wait, I thought we were talking partial F. Well, we got to understand what an F test is. The point of an F test, Oh yeah, Kayla, feel free to ask. And anyone feel free to ask. We just put questions in the queue, so keep asking your questions. So the point of an F test is to go, sure, green, that works. I got to reinstall Word. The point of the F test is to do this. This is the ANOVA or F test. So this is an ANOVA. The reason it's called an F test is it uses the F statistic. So like a Z test uses the Z statistic, a T test uses the T statistic. ANOVA, which is analysis of variance, which tells us where the variation is coming from or the sources of variance, is going to be understand the code in the partial F. I'm just not sure I was playing layman's. Yeah. That's definitely, you bet. And so this is the F test. This is a full F test. And this might help right here. Tell me if, especially after this right here, tell me if this makes sense. Like, how do I explain it without using sum squared? Oh, yeah. No, that's, so what is the F test doing? It's seeing if going from the naive to the full model actually is worthwhile to us. Like, just think about not using statistical terms. Like, we're seeing if there's a statistically significant reduction in the sums of squared error of going from the naive model, which is the mean of y, going to the full model. So the naive model is the mean of y, at least with quantitative models, more on categorical models in 2 or 3 classes. But with a quantitative y, the naive model is the mean of y. And then we're asking if there is a significant, like unlikely by random chance, statistically significant, reduction in the sums of squared error, the errors that the model makes, going from the naive to the full. Now that's the mathematical, statistical way of talking about it. But what are we really asking here? We're asking, is there reason to use our model? Just think about it like, is our model better than just using the mean? So without even using statistical terms, the mean is technically a statistical term, but you could just say, is our model good? And if you have an ANOVA with a p-value that's low, you say you have evidence to use your model because there's a reduction in the sum of squares that's statistically significant. But the full ANOVA is always doing the naive to the full. And by looking at the p-value here, you're just asking, is our model better than the naive? Does that make sense to just say it that way? Is our model better than the naive? Like, do we have good evidence via statistical significance that our model is better than the naive with the full ANOVA? So the full ANOVA is always done for you just by running the model. Like, we have a model right here. The full ANOVA is right here. Let's remove the graphics. And in very layman's terms, so, yep. So just go pure layman's. I'm gonna drop my pen. In pure layman's terms, this p-value right here, which is the ANOVA, because we see the F statistic denoting that this is the ANOVA right here, this is telling us our model's better than the naive. Like, just pure layman's, like, the no variable model, which we can make the no variable model by doing this, bet people didn't know that. There's the no variable model, which doesn't even give us an r squared because the r squared would be 0, and the intercept is this because it'd be a flat line. If we plot this model, it's just the flat line. That's the mean of y. We can even confirm this by going right here and seeing that that is the mean of y. So the mean of y would have that right there, and there's the intercept, and there's that. That is the flat line model right here. Awesome. Let's throw 50 points right here. Samantha and Bailey helping each other out. Vols help Vols. Yeah, sometimes let's just literally switch browsers because it can be like a setting in one of your browsers. So can we say that we should use the complex instead of the simple because I mean, you could just tell me, if you feel like your answer was good enough and the graders take off points, just tell me. Like, if you give a good answer, I think if you're going to go not statistical here, because now let's start talking. We know that the F test is comparing the naive model to the full model, and we see via this output right here that we have a statistically significant model. Even though it's a one variable model, it still is an F test. But now let's go and let's put back here a one variable model, and I'm going to call this simple right here without the O. Usually we don't spell it with an O. And I'm going to call this complex. Complex model is going to be absolutely insane with a ton of variables. That is how you get all variables in here. And so now let's go ANOVA, simple, complex. And this is exactly what you're doing right here, Kayla. And we'll talk a little bit about this output, but let's first visualize what's going on right here so we can see the visual of the partial F and understand what it means to be doing a partial F. When you do a partial F, you're no longer starting at the naive. Think about it as you're going part way of the distance. So we'll go here with blue. And so a partial F is going to start with a simpler model. I thought that was blue. Simple model right here, which just has less variables. And then you'll go up to a point of a complex model. So the point of the partial f is not to start at the naive model. So this is now a partial. It goes part of the way. So once again, think about the ANOVA right here with the full F test. You're just saying, is your model better than the naive? That's all you're saying. You're just saying, do I have reason to use my full model? And if the p-value is low, you use the full model. If the p-value is not low, your model's not better than the naive. So, or you just say my model's bad. Like that's non-technical way. If you get a bad p-value on this, you just say, this model's not good. This model is not worth using. It's like, we're talking statistical terms, we start saying like, it's just as good as random chance because the naive is just the mean of y, and we're not explaining any better than the naive. But it just non-technical terms, as non-technical as I can speak, if you get a high p-value for this test on this side, then you would say like, my model is bad. If you go over to the other side, do I have another side over here? You know what I'm going to do? I'm going to do something crazy. Watch this. Camera, watch this. We'll go here, and we're going to go here. We've done it. Oh, I duplicated myself. And now we'll go here, transform, flip. What? What's up, Brian? Okay. So go over here, and we're good to go. And I can't shut off both. I think, yeah, if I want to make another side for me, I have to do something crazy here. Okay. This might do interesting things when I hit the button now. I better watch out. So this over here is asking what? Like this is, if your p-value were to be high over here, what would that mean? If your p-value were to be high over here, what would that mean? So think about the instance where your p-value is high over here. So a high p-value would mean what? Your model is no better than what? I definitely mentioned the p-value. You do kind of have to mention that. I know the p-value is technical, but it's big in the decision. So, because you don't really have to explain like the probability of our results are more extreme by random chance variation to achieve a sums of squares reduction of this larger or larger would only occur this % of the time, given that there is no difference between the simple versus the complex. Use the simple model, high p-value, simple with high p-value. Use the yeah, exactly. That is as layman's, and that's perfectly fine. Like that is, we should understand that instantaneously. And so here, I'm going to explain exactly what Kayla said to make sure everyone hears it if you're watching this part of this video. When the p-value is high, you'd use the simple over here, which is the same for the other side of it. If the p-value is high over here, you'd stay with the naive. When the p-value is low, you'd go with the complex. When the p-value is low over here, you have evidence to go with the full model, like your model. So it works the same that when the p-value is low, you'd go with these up here. When the p-value is high, you would stay down here, which is the inverse of how this graphic is drawn. Like you go to the other side. And so here's the technical side of it, which I probably wouldn't put this in your report. When the p-value is low, you're saying that the sums of squares reduction by going from the simple to the complex is unlikely by random chance. To achieve a sums of squares reduction of that much or larger by random chance would be very unlikely, given there is no difference between the simple and the complex. So the null for this test, if you think about a null hypothesis, is that the simple and the complex are just as good. Like the null over here could be that the naive and the full model are just as good as each other, that the naive and the full model have no difference. The alternative could be that the alternative is that the complex or the full model is better, like we should use the complex or the full. So, and we try not to go, like we don't try to write out nulls and send people our null hypothesis here. We try to maybe say to them, well, you know, I ran a test and it showed me that the complex model is better to use, that we should use the complex model. And what we're saying to them is, I ran a test, achieved a low p-value that suggested to me that the sums of squares reduction that we were receiving going from the simple to the complex is unlikely by random chance. A sums of squares reduction or reduction more extreme. That's how p-values work. The probability of our results or results more extreme happening by random chance variation. Oh, it changes that one now? Well, that's not good. Let me remove. Brian, you have to go. This Brian is being removed. Brian, no. Oh, now it does not interact with my... Well, that was not a good idea. 2 seconds. I'm going to fix this here. technical side with Brian Stevens. Oh, no. Oh, maybe I have it off right now. Technical side with Brian Stevens. There we go. Technical side. Awesome. Other question. I used equation for the model, but I didn't print it. Oh, wait. Used. Explain more in detail, Kayla. Explain more in detail. And I'm going to go over here to this. This is what we see right here. So for those wondering, the example, we would use the full model right here. The full model is pretty crazy. The full model has all of these variables. I'm not saying it's the best model right now, but as of right now, with this p-value, we have evidence to use the full model right here, the complex model. Sometimes I call it the full, the complex. There's other names for it, but it's just a model that has more variables than the simple. So going from the simple to the complex achieves a sums of squares reduction that is unlikely by random chance. Here's the sums of squares reduction. Here's a standardized version of it via the F statistic. And there is the probability of R reduction or reduction more extreme occurring by random chance. And the main thing to know from this, which Kayla and I were reviewing, is that going from the simple to the complex, which is this whole model here, is achieving a sums of squares reduction that is unlikely by random chance. So the most simplest thing to understand is we have good reason to use the complex model. With that p-value right there, that's saying, yeah, the complex model does better by this. I tried stars instead of the X's, but it wasn't. Oh, yeah. I see what you're saying. Yeah, exactly. So what happens is, I see what you're saying. Yeah, I get it now. Let me go 2 seconds. Class is over screen. Gotta make my own thing for this. I know exactly what you're saying. And I'll explain why. Okay. So Kayla is saying, here, let me put a cut in the video. This portion of the video right here, I'm talking to Brian in the future. We're talking about LaTeX or LaTeX coding and how it works in RStudio and how you can get some interesting things when trying to write equations. So let's go take a look at that and talk about some LaTeX or LaTeX. I think 201, if you have any questions, let us know, 201. Bailey was here. Leslie, Bailey, Samantha, if you have any questions, let us know. We definitely, and Kayla, keep asking questions. That's what we're here to do. So let us know. I'm always trying to line up more questions. So, you know what's, Kayla, do you want to see something really crazy? Check this out. This button right here, I just found this out watching things on LinkedIn for RStudio. You can go to Markdown mode right here, and I haven't even tried this much, but this is Markdown mode right here, which lets you view it as the Markdown file you're creating. And so we should be able to go to Insert, let's go Display Math, which puts in the double dollar signs right here. Which I haven't tried this before, but I'm going to take your equation right here, and Kayla is now using the x's instead of the, so there it goes right there. Now, using the x's is totally fine. And of course, with mathematics, you don't have to use, so if you do the display mode right here, which is found via this, and I just found that out yesterday, I think. I was watching some videos. I'm always trying to update my knowledge and find out more things about how to use R in RStudio. Yeah. Oh, use the stars. Yeah, the stars will bold things. Oh, whoa. It actually like changes it to that. Whoa. So if you use star right here, that creates bolding. So hello. And now you should see, will that not do it? Oh, is it actually like doing without, how does that look right? That's awesome. Okay, so stars are special characters. And so because if you use stars, it'll do this right here. It's creating bold around that. So the backslash removes the special character capability. So if I were to go to this markdown mode and probably type, see, there's the bold hello, it lets me see it. If I were to type $, okay, it is opening that up. But to not get the special character version of it, you have to remove its superpower with a backslash. And now, so this is just a little bit on Markdown. If you notice right here, it's showing me what it's going to look like. This button right here lets you see what it looks like. So if you notice there's not backslashes before it, because the backslash removes the superpower on it. I call it like a superpower when I talk about it. So, but the X's look like variables, not multiplication. So I think what you want to do right here, if you want to go right here and you want to do multiplication. I think it's this. Try... No. No. Give me a second. I think that's how you do LaTeX stuff. Yeah, you see it's registering that. Okay, that might do it right there. Yes. Okay. So if you use a star... Oh, it's doing it. That seems to work right there. Let me look up multiplication in LaTeX. Okay. Multiplication sign in LaTeX. Multiplication dot in LaTeX. I don't know if you... It's... Oh, wait, C dot. And it's backslash. Okay. So they're saying do this right there. There we go. So if you really want it to look nice and neat, which I've had students really go, because a lot of people use LaTeX. LaTeX is a very, very common. Yeah, they were curly brackets. That's how you call, if you, here, I'll show you some neat stuff right here. So that looks like that right there. If you do things like, I'm trying to remember how to do this. What is it? My brain doesn't work. We should just be able to do this right here. No. I see, that's why it's doing it. How do you divide two things? Create fraction in LaTeX. Let me see how to create a fraction in LaTeX. I forget these things. They're not... Oh, there it is. \frac. Okay, so the way LaTeX is a little bit different of coding. The backslash calls the function. And so now... Is it not backslash? And then... There we go. There we go. So pretty interesting stuff right here. You're not meant to be a pro in LaTeX, but... So these are curly brackets, and you can see what's being displayed right here. And that's one of the neat things about this new mode that I just found out in RStudio 1.4 is you can then actually view it right here and see the inline equation. But you can also write this out right here and get what you want. So I could go right here and do C dot, and then do, there we go. So you can write stuff like that right there. So don't worry, you can do this in Microsoft Word at the end. Yeah, exactly. And so this is, I think it's super cool. Like, this is the kind of fun stuff I like just learning in my spare time. It's neat that we've got this markdown mode, which I just found out about. I'm always watching new videos on what there is. One of my goals as an educator is to stay up to date with what things are doing. So hopefully I should know like all the buttons, right? I should be like, I can tell you what everything does, but I can't. There's so many updates and things changing and LaTeX and blah. So the way to think about LaTeX, we're not meant to be pros in LaTeX. You can always Google things like I was just Googling, and I know some LaTeX here and there. Yeah, a lot of people think this is way easier because you can just like type it out. You don't have to like search around for things. If you know the name of what you're using, like if you're someone who makes a lot of equations, you can just type \mu and it'll give you mu. And we should be able to do, can I create a new variable with category? Yeah, like female smokers, female non-smokers. Yeah, that is going, yeah, I like that a lot. Do that. Check that out. See if that, yeah, create a combination of like subgroups and make a, yeah, I like that a lot. That's a really great idea. We should be able to go here and do the following. Let me try this. It's SQRT, I think. Oh, curly bracket. SQR? No! How do we do square root? I swear it's square root. Square root in LaTeX. SQR. What? Is it mad about that? LaTeX. Look at that. That's the square root. I was sure of it. Oh, and then I think I know what we need to do. If we want this to be, we have to go here and go here and do \frac. There we go. There we go. There we go. Yeah, it just takes practice. It just takes checking it out. Yeah, and so what's interesting is that's the square root function for R, and it's also the call to make a square root in LaTeX coding. So we're not really coding in R. This is have you heard of LaTeX before, Kayla? It's like the language for writing out these reports, and so it's a decent thing to learn if you're going to do like reports. If you want to do research and stuff, a lot of people do their reports in LaTeX. So it's a decent skill. Not something required for the class, but kind of neat stuff to examine and understand how to use the lot. Yeah, it's definitely around. And so I really, for students interested in it, I definitely suggest learning how to do some LaTeX coding, but it's not required. You can just do it in Microsoft Word if you want. Like everything we just did right here, we could go to a new Microsoft Word document, and we could go here to insert equation, and then you go here and you do this, and you see I've done this so much that I'm way used to this. Like I know where everything's going to be at because I'm everything. There we go. And then we need to put that inside here. So I've used Microsoft Word equation editor a billion times, literally a billion times. So if we want to make the same thing in Microsoft Word, we can do that. So as long as you have a skill set in writing equations, you are good. But doing the same thing over here, I heard weird noises. It's birds. I can't figure out how to create a new variable. I was thinking, what's really, you want to see something really crazy here, Kayla? Let's use your example. Let's put a cut in the video. Let's talk about some variable creation right here. So we're going to talk about some 320 variable creation, Future Brian. Future Brian, put those marks in the video for later, for when people need some help. Let's talk about some variable creation. I'm going to open up a new document. Let's go over here and let's do some variable creation. Here we go. I don't understand. Streamlabs, why can you not handle this? Streamlabs OBS can. It seems like we're streaming well today. I don't know. I'm going to reset the router this weekend. I'm going to try to reinstall Microsoft Word. I've got a whole list of things that need to happen, but let's make a new variable. Let's go here to data ex2 on tips. There we go. We got the data set loaded in. Let's clear our environment and let's clear this. Brand new RStudio. Who dis? It's ex2 tips. That's who it is. So yeet. Yeet. Let's get out of there. I'm going to move. Yeah, we're good on this. Okay. So having some fun here. So not a lot of fun. No buffering. I like that. I see that buffering word. That's the scariest word to me. We have gig speed internet. Like for those who be like, Brian, I need to get better internet. I promise you, like, watch me doing a speed test. Our speed test, run speed test. There's the speed test right here. We're getting half a gig down, but what really matters is your up speed. We're getting 38 up right there. So half a gig down, 40 up, and you only need about consistent. Consistent is what matters with streaming. So we have a really good router, really good modem. You bet, Bailey. Feel free to ask. Let's do that next. You got it, Bailey. So check this out. Let's see something right here. You ready? Let's go and I'm gonna attach it. Attaching. I like it, Dr. Petrie. He's not a fan of attach yet. I'll win him over to attaching stuff. I just buffered. It might have been the speed test. The speed test might have been taking a bunch of the bandwidth and caused some inconsistency. So we shouldn't have network congestion either, because generally I'm the only one here at this time. So you know what it could be? Oh my God. It could be the PlayStation 5 somehow taking, it didn't happen until we did. It might have been me doing the speed test, but I might try something like unplugging the PlayStation 5 or something. The PlayStation 5 shouldn't be doing anything, but the only thing that's really changed from last semester to this semester is we got a PlayStation 5. So if the PlayStation 5 is like going online looking for updates and taking bandwidth, that could be the issue. So maybe the PlayStation 5 is causing buffering issues on the stream. That's the only like new technology we have. So you have to think what's different, and maybe that's it. So when we're going to make a new variable, check this out, Kayla. This is not what I would suggest. Here's what I would suggest. Let me do what I would suggest first, lest everyone do what I'm about to do. You can literally make any new variable here. We can take Bill and divide it by this right here. When you make a new variable, I guess I already have the names, but when you make a new variable, we can just call this variable name X. What I'm going to go here now is I'm going to call this new variable, and this is 100% acceptable. I mean, don't do it. You're not going to get count off for doing exactly what I did, but that just created the ratio of somebody's bill to their tip, which actually is not probably the worst variable. So this right here is the ratio of someone's bill to their tip. It has now been appended onto the data frame over here as new variable. So we could call it something different. Like, let me do this. I'm going to remove it. You can remove that by going here and typing null and watch behind my head. It went away. So you can remove variables. Good to see you here, Mary. We can do some 201. We're going to do, I think Bailey had a question. Bailey, whichever one you want to do, we can definitely do it. Or I can do a random one if you'd like. Exactly. Good to see you, Mary. So you could call this something different. You could call it like ratio bill to tip. A study, you bet. We'll do that one next. You got it. So what I'm doing here is I'm just giving it a better name than I gave it before. You bet. Let's do that one next. In about 3-4 minutes or 5 minutes, we'll be doing it. So, and thank you so much. I really mean it. Like, sometimes I do office hours and like it's very quiet and I'm like, anyone have questions? So here we are with the new variable in there, the ratio of the bill to the tip. So you can do, I think that works. And then you can take a look. You can see how well it works by putting it into a model, which email me if you have questions or mention that you have questions. I also did tip, mean tip. Ooh, that was interesting. Oh yeah, how they did compared to the mean tip. That's really interesting. Yeah, that's a great thing to do here. So you could look at the tip compared to the mean tip, all that great stuff. I'll just show what Kayla did right there. She took the tip in USD. So tip in USD and then compared that to the mean tip. So kind of seeing, the ratio of somebody's tip compared to the mean tip. And so now we could say here, compared to mean tip. So what we have right here is compared to the mean tip, how someone tipped. And you can see if people were below the mean tip, above, and this is the amount they tipped, right? How much they tipped compared to the mean tip. I squared it though because it's NA before squaring. Oh, there's NAs. Ooh, let's look at the variable. We have it stored here as X. And are there NAs? And then we can talk about why there's NAs. I don't see any NAs produced. I'm trying to think why there would be NAs. I squared it though because it is NA before squaring. I didn't get NAs here. Would there be this takes the mean of it. You might have done a different one which was missing. In the summary it was NA. It was all, and so it looks like we achieved it. You might have done slightly different variables. I'm interested. Feel free to send me it on Discord, your code, and I'll see, because I'm getting slightly different. But as long as you append a variable onto this, you're good. Does that make sense? Like, this is the goal right here. And don't worry, you're not trying to find the best variable in the world. And then I'll show you how to create female smokers, which we can create pretty easily here. But as long as you create a variable here and can add it to the model, you're good. So we've created two variables right here: ratio bill to tip, compared to mean tip. And we've given them logical names. So this achieves the goal. Don't worry, if your variable is horrible, it doesn't matter. The whole point of variable creation is to understand that we can create variables and do what we're doing here. Like, we have achieved the goal of doing this. It was all good in the data set. The results were NA in the summary. Oh, I know why. You added it to the model, right? So in the model, what you're saying when you add it to the model, that means that it brought in the exact same variation that the other variables were already accounting for. So maybe you've got, because if you create a variable from a variable just in itself, it looks like, yeah, this is the, hey, if you find something really amazing, tell me, which then I'll tell Dr. Petrie and be like, hey, did you know this thing about this data set, that there's this variable? Which is kind of, I'm thinking how this might, you know what this is actually? This is a bummer about this one. This right here is actually a standardization of this variable. So we really, don't worry, Kayla, do not worry. We really haven't done much for variable creation right here because we've just standardized it. And you think about it, because dividing by the mean, we've set now the mean tip to 1. So we've standardized the mean to 1, and then things. So it's a standardized version of it. So we actually haven't changed the variable, and it's a new variable, and it's a new way of talking about it, but it doesn't bring in with it new variation. And another way to understand this is to say we could just take this value right here, and we could just turn it into a what. All of these now are what's. By scaling it, which is a really great function, all of these values are now what? All of these values are now what scores by scaling it. What does the scale function do? So by doing this right here, and let's go right here, and we'll call this, so I'll give away the answer. So z-score tip. If we were to go here and go to a linear model and predict, let's just predict bill right now, bill in USD by tip in USD, and z-score tip. So, oh, that's cool. And z-score tip and data equals ex2 tip. We are probably going to see the same thing you saw where we have NAs in the model. And the reason you get NAs in the model is because it doesn't bring with it new sources of variation. And so the z-scores are the same. It's the same data, but it's been standardized to, and this is very important for data mining, it's been centered to 0, which means we shifted the distribution over to 0. The center's been moved to 0, and the standard deviation's been moved to 1. So the z-scores do not bring with them new sources of variation unaccounted for by the other x variable. Yeah, and so here we go with the categorical one, and then we're going to do some 201. But what you're asking for is really awesome, because if we go to if else right here, and so I'll put this in the chat too, and don't worry, I just don't want people in 201 or 320 to be like, this is what I have to do. No, this is like advanced, and I love doing the advanced stuff. Let's go here and look at ex2, and let's go here and do the following. If this is gender, then let's go right here. If equals, is it female? Let me look at the variable the way it's named. Female and male. Okay, cool. If it is female, if the person is female, like talking about objects here. So if the person is female, then we go right here. We also go to an if else, and we go here, and we're going to go to smoker. Is smoker yes, no? I mean, I know it's yes, no. How's smoker? It's no and yes. Okay, with capitals. You have to make sure you get the smoker is yes. Then we go here and we say female smoker. And if not, we say female non-smoker. Okay, there it goes that. Now we put in the second no argument. And then we go right here. Cool. And if, there we go. Male. This is, we're in the no statement. This looks very complex. It's two if else's. Yeah, nested if else's, exactly. So this is just, of the first if else, this is the true section of it, and this is the false section. Does that make sense? Like if we make this look smaller right here, the first thing it's going to do is go into here and see if the person is female. It is true, it'll run this code. If it is false, it'll run this code. Does that make sense on how I've nested this right here? So when we enter into this, it'll say, look at the gender right here. If the person is female, run this portion of the code. If they are male, because we only have male and female in this data set, if they are male, run this portion of the code. So just looking at it this way right here, we can see that if they are male, we're going to enter into here. Then we're going to ask, are they a smoker? If they are a smoker, because here's the true statement for this, we're going to put male smoker because we're in the false portion of this question. So they would be male for this right here. Yep. And then there's the female portion. So when we run it, we get this vector, but we need to do one more thing. We're going to go here to factor. That turns it into a factor with 4 levels. Then we're going to go right here, and we're just going to call this X for the time being to make our code not so crazy. We're going to go here to, we could store it, but we'll go here to males. We'll say gender smoker. And gender smoker, we'll go right there, call X, and we should have a categorical variable down here at the bottom. Categorical variable with 4 levels. There it is. That's how you create it. There is the categorical variable with 4 levels created by nested if else's. And I would say this, if you were able to write that code, you are pretty good into 474. Like if you were able to think through that and create that right there, and that's the power of coding. Like no matter how big this data set is, we can just go in and recode it. Yep. Let me drop this in the chat, see if it fits. Is it less than 200 characters? Oh, it's right there. It's at 198 characters. So, and I also tried it. One thing you could do is you could go right here. You could do this like this to see where it's kind of going into it. Just depends on how you want to do your spacing. But some people might choose this right here to say you enter into this. If they are a female, you'll enter into this. And here's the yes, no on this. But if the false was right there, you'd enter into that. Yep. And we try to do it in little bits because it can get super complex. Probably the best way to do it in is going to be to go here and go to if else. And we're going to do 320, 201 right after this. I'd start by running this, and I would say this right here. I'd run this, and then you can identify that. So now you think about, okay, we're in the female statement or we're in the male statement. So now if you divide it up this way, you would have this. So these are all females right here. Like these are, at this point, you know everyone here is female because if gender is equal to female, print female. That's what this does right here. This person is female. So it'll say now this person is female. So whatever I put right here, it'll do. And so what I want to do now is I want to go to all the females and I want to run an if else right here, which is then going to do a test on just these individuals. So hopefully seeing this in is going to hopefully make us understand that we're now only focusing the if else on these individuals right here. So you could ask, like, watch this, ex2 tips, tip in USD greater than 10. Let's go here to, we're still here, and let's go here, big, let's go here, female, great tip, and female okay tip. And you see here, we can see where the big tips are. Oh, we don't have any, probably because I went way too high. There we go, female great tip right here. So, hey, Adam, what's up? Good to see you here. We're going to hop over to some 201, but feel free to ask some questions. We're just showing how to do some nested if-elses. This was variable creation. Let's hop back to Spice. We're now hopping over to some 201. Here we are with 201. We're going to do the 201 waist size question. Researchers measure the waist size. A study measured the waist size, finding inches. Hey, here we go. Let's do it. Feel free to ask any questions you got. Hi, yeah, feel free to ask. Hi, here's a 201 question. I just got the call, Emily. Oh, that's all right. I hope Emily's doing better. That's totally fine. Great questions today, and I hope your little one's doing well. Let's hop right here and do this question. So when we look at this distribution right here, how does this distribution look? This is something we should be like, boom. We draw our little dudes. We draw our little dude right here. How's our little dude look? Right to the low, left to the low, right to the high. 310 exam tomorrow. Good luck on that, Adam. Skewed. In what way is he skewed? Right to the high, left to the low, whatever way the tail goes. Right to the high, left to the low, whatever way the tail goes. Skewed to the left. There's our dude. Right to the high, left to the low, whatever way the tail goes. Skewed to the left. Always try to draw the little dude because sometimes people forget. So he is skewed to the left. So these simulations right here, what are these simulations? Let's take a look. These simulations are the central limit theorem. I think we can zoom in on this a little bit. Darn it. Yeah, it's good. All right, so when we look at these simulations, this is when you take a sample size of 2. This is when you take a sample. Ooh, how's that starting to look right there? Like, remember, it was skewed, but as we take larger and larger samples, the distribution starts to look more and more what? Like, I can still see a little skew here. I don't really see much skew here. And by here, I don't see any really at all. And that's impossible to see the skew. Distributions are becoming more normal. And this is the idea of the central limit theorem. The central limit theorem is going to say to us that as we take larger and larger sample sizes, we would see that the distribution of the mean of sample size 2, mean of sample size 5, mean, there's the mean, of sample size 10, the distribution of the mean becomes more normal and also becomes water. If you notice, this starts at 28 and goes up to probably 42 or something like that. Goes to 30, goes to 42, goes to 32. It's almost like it's becoming more normal and water. It's becoming more normal because it's covering less of the number line. So the two concepts are that the distribution of the mean, as we increase the sample size, the mean, as the sample size increases, will become more normal, which we can see, and it'll also become water. Because look, it starts at 28, and by down here it's at 32. It's not even starting there. So it's almost like it's becoming water. Because it was at 28, now it's not even there. So the distribution of the mean of the sample size increasing is going to be more normal and water. These simulations do appear to show the central limit theorem. Good simulations will show what they're meant to show, so they do appear to show it. The central limit theorem, which states it is shrinking, it is decreasing. Great job, Hi. They show all these histograms centered at 36 because the mean does not change. We were talking about that earlier today with the following. Here it is. The mean for the distribution stays the same. There's the top portion, and the standard deviation is going to decrease by the square root of n. So you can see right here, as we increase the sample size, the mean does not change. So wherever this mean is of the distribution, the mean would stay in the same spot. I could probably just draw a red dot a lot quicker than I could copy paste them. If this is the mean of the distribution, it would stay at the same value. So the mean might be something like, let's say, 10. The mean would stay at the same value, but the standard deviation is going to shrink. If the mean is at 10, the mean would stay at 10, and that's what this top portion right here represents, is that the mean would stay the mean as we go to higher and higher sample sizes of sample size 100 and doing the mean for 100 observations, which would be taking 100 individual dots and finding the mean and doing that repeatedly. So we would see that the mean does not change, but what does change is the standard deviation, and we are observing that here, that the histograms become more normal, the central limit theorem, so it approaches the normal shape. Let's go look at that. Oh, hey, Mr. Dude. So it approaches the normal shape right here. And what else? And the variability in the sample means is doing what? The variability is the standard deviation, and you can see that right there in the equation. The variability in the standard deviation is getting smaller. We can also see that right here that the distribution is getting tighter, which is literally this portion of the equation. So the variability is going to decrease, and the histograms appear to show are fairly normal by the time they reach 5, because this is barely skewed. So with barely skewed, it would take a very small sample size. And this goes back to the large enough n condition. Just to show these notes here briefly, the large enough n condition, let's hop over to lecture screen. The large enough n condition states that the more skewed it is, the larger n needs to be for the distribution to be nearly normal. So the more skewed it is, going from normal, we need 1. To skewed, we need 25. To very skewed, we need 100. The more skewed it is, the larger the sample size. The less skewed it is, i.e. more normal, the smaller the sample size is needed. We can check the skew of it via the histogram, the normal probability plot, or the goodness of fit test. And to see what that looks like, let's go to a slide with that really briefly right here, where we are checking either the histogram, the first way, the normal probability plot, or the goodness of fit test. And this passes via all 3 of those conditions. Histogram looks unimodal and symmetric, which is normal. Normal probability plot follows the line right here, which is the normal. And then right here, we see a high p-value, which high p-value is greater than 0.05, greater than or equal to technically. We're going to say that that means we still believe it's normal. We do not reject the null. More on that next lecture. But that's this question. Hi, feel free to ask some more questions, or Adam or Kayla left. She had to go. But what questions are there? And great job, everybody. We'll hop here to space. We'll listen. We're not done yet, as long as people have questions. Gonna maybe eat some lunch here soon. What questions are there? Background just breaks. Let me try something with the background. While everyone, feel free to ask some questions. Oh, Haley's got a question. Good to see you here, Haley. Could we do this one next? Assume the duration of human pregnancies can be described by a normal model with a mean of this, a standard issue of this. You bet. Let's go to the question. Oh, that's all right. Adam, that's quite all right. Do not worry. We drop a few assignments. Perfection is not needed. What we try to do is we try to do a consistent work. My Pearson's being weird. Here we go. Thank you, Haley, for the question. We'll let the music play in the background. So here we are with Haley's question. Assume that the duration of human pregnancies can be described by a normal model with a mean of 266 and a standard deviation of 11. Awesome, Adam. What percent of pregnancies should last between 260 and 275? Now, where are we going? Does everyone know where we're going to go to get some exact answers on this? We're going to speak to our old friend, Mr. David M. Lane. A dude made an applet named after himself. Now everyone says his name. Smart man. So right here, Mubot says go here. Well, don't mind if I do, Mubot. So here we go. There is the David M. Lane applet, and it told us that it is normally distributed. So we passed the normal. We passed the normal distribution right here, like, because it says it's normally distributed. So I mean that it says it is normal. So that means it is this. So we need to put in the mean and standard deviation. I'm going to zoom out a good bit just so I can show you down here on this applet. I am putting in 266 and 11. That's what I'm putting in. I'm going to put it in both spots, which sometimes can help when you're doing questions to have it in both spots right there. So that is the mean and the standard deviation. David got me 100s. You bet. David M. Lane, dude, you're awesome. We appreciate you, David M. Lane. He's got a statistical consulting thing right down here. Like, I wonder if that's him. I should call him up and be like, thank you for your applet. And he'll be like, do you need consulting? I'll say, no. He say, okay, thank you. Bye. So we got the applet right here. This shows us the pregnancy durations. And you just think about this. Pregnancies we know last 9 months, 3 trimesters. So 3 months looks to be about 266. If you times, 30 by 9 months, I meant to say, you get about 270. So it's about the length of a human pregnancy right there. I mean, months have different days in it, February versus December. Hello. No, okay, bye. I want to speak to David M. Lane, made the applet that we use. So we want to ask, let me ask you this. About what percent of pregnancies, and just you can say less than this, about what percent of pregnancies would last more than 299 days? I'm not going to show you the answer, but we can see here visually, or let's say 300 days. About what percent of pregnancies would last more than 300 days? And you can see the answer visually right here. According to this model, what percent of pregnancies would last longer than 300 days? Just maybe explain to someone without giving them the exact answer. You would probably say, you could say it like without words. Without numbers, I should say. You need words to speak. But about what percent of pregnancies, and that's the answer. And you can see it's 3 standard deviations above the mean. So you'd probably say next to no pregnancies, or like less than 1%, or maybe probably this is going to be about 0.001%. I'm going to say 0.001. There it is. 0.001. Very, very few. One in 1,000 pregnancies would last more than 300 days according to the normal model. And that would be an aberration. It would not be very common. So our question is asking something similar right here. It asks what percent of pregnancies last between 260 and 275. So we're going to do the same sort of idea and go between, let me get the numbers. Those are very important. 260 and 275. So we go right here to 260 and we go to 275 and we look at it for a moment. And we know between here and here is 68. So you might say, how could we ask you this on a test? Well, if you were to graph this out visually, which we can do by drawing this because we just put the mean and go up standard deviations, I know the answer down below has to be less than 68%. It's probably going to be about 47%, but it has to be less than 68 because between here and here is 68. So I'm going to say 48%. I should just guess 50 on the dot. If I had guessed 50, we would have gotten it right, 50.07. I was close. 48% is close, but I should have just said about 50%. So 1 decimal, that's going to round to 50.1. Just make sure to round it properly. What is the longest 30% of pregnancies? So the longest 30% of pregnancies is, funny enough, it's going to be around here, right there. It's going to be right about there, which is going to be about 272. Yeah, about there. But we don't need to guess. We can just go here and we put the numbers in and go to the longest 30% of pregnancies, and 272 was a decent guess. I knew it's about here because I've used the curve a lot, so I know where the top 25% is, and I guessed where the top 30% is. So the top 30% is right here, and that's the number. We're going to copy the number, and we're going to go back here and paste it, round to 1 decimal. So might have got it with 272. Decent guess. Suppose this is where the question changes. Now I want to point out the deal with this question. What's the deal with this question? This question up top is just chapter 5. It's a chapter 5 review. This right here is chapter 14, where we're talking about 80 pregnancies. So this is where it changes, and we need to write down the equations. No longer is the distribution going to be described by just a mean and a standard deviation. We're going to have here a mean and a standard deviation for the distribution of the sample mean of 80 pregnancies. And we have here that the mean for the distribution of the sample mean is equal to the mean. So it's going to be the same value. It's like, wait. But here, the standard deviation is going to be divided by the square root of n. So we need to take the original standard deviation divided by the square root of n. So this will change the distribution. It'll change the way it looks. So let's go right here, go to some purple. The mean was 266, and so that does not change. And the standard deviation was 11, but now 11, space pen is back, it's taken over. Divided by the square root of 80, and let's go ahead and solve that. 11 divided by the square root of 80. You know what I could do? I don't know if that would do it. Let's go square root of 80, and there we go. And 11 divided by square root of 80. So that's the new standard deviation, 1.23. I'll round it for once in my life. There's the new standard deviation. So what I'm going to do now is go back to my applet. I'm going to put in the 1.23 standard deviation, and this is for a sample of 80 women. This is the mean and the standard deviation for a sample of 80 women, and it goes by what we've been mentioning throughout class today, or lecture, or office hours, is that this distribution is tighter and more normal. It was normal to begin with, so it'll still be normal, but it's also tighter, and that's where we did the sigma over square root of n. So we now have a more normal, it was normal to begin with though, distribution that is also tighter by a factor of the square root of n, because we're doing a larger sample size here, and we use that sample size n to figure out the new standard deviation for the distribution of the sample mean. So many words. And let's go ahead and take a look. It wants the mean. Well, the mean is the mean. So the mean was 266, and it wants the new standard deviation, which we calculated right here. We're going to copy paste, round to 2 decimals. And then what percent of the probability, what is the probability that the mean duration of these pregnancies will be less than 269? Oh, yeah. Let me send you that in the chat here, Mary. You got it. What's the probability to be less than 269? The probability will be less than 269. We go here, and we go to below 269. And, oh, wait. Oh, really? Wow. Basically super duper likely. Round to 3 decimals. Could we just put 1 right there? We should get everything right. Could we have just put 100%? Is the plus or minus going to work? Oh, that's a bummer. One thing I don't like is that you get them wrong if you add an extra decimal. I've always disliked that about their questions, and I feel like we should improve that. So it's one of my goals is to go through, and we'd have to probably make our own versions of these questions. So let's change topics. Time to change topics. So Mary, we've got some really great videos right here for the visualization. Let me put the visualization playlist in the chat. So here it is. You're hearing Brian Stevens in the background right there. Got Rick and Morty on this one. Drop this over here. Talking about visualization. You're welcome. Great job, Haley. So, yep. And let's hop over to the main screen. We got some Rick and Morty right here. Rick and Morty in the chat. So check out Rick and Morty right there. It's got one of my favorite, like Brian and Jason, and then it glows. But you really want to check out the real deal. I won't ruin the surprise. Well, we'll ruin it a little bit. But so the visualization playlist is in the chat. Go check out this one though, for a lot of fun. Check out the following visualization, going over how to do the true mean. And yes, have some fun right there. Lots of different intros. Yeah, spending, I don't know, the memories of doing visualization intros. Yeah. So that effect I actually use. I use that effect for some stuff. Where am I using it again? Oh, it's used, this effect right here, this glowing effect moving downward is actually used in the speedrun videos. If you look at the speedrun videos, you go to the speedrun videos and you take a look at them. At the very start right here, watch the glow effect over here. You'll see it, that effect right there. So that's the same effect being used in Adobe After Effects to create the glow effect there moving. This took a while, like this grain effect and everything, and this screen right here, that didn't take that long, but the that took a lot of time because each of these are their own elements. Finding the fonts, yeah, that took a while. Yeah. So yeah, I don't know. I'll reappear. I have fun making them, but I'm like, man, maybe for sometimes like 2-3 seconds of a video can take 2-3 hours. And this is like, yeah, those parts of the video take the longest, but they're the funnest parts of the video. And they look, I don't know, I was very happy with how that turned out. And then, so there we go right there on that. Yeah. If you have questions, let me know. Let's do this. Just in case anyone, can you explain how to find the Z-score in Visualization 7? Yeah, is it, does it want you to find the Z-score? I forgot if it did. Let me go look at that. Let's get serious here. Let's go look at some Z-score for visualization number 7. Let's go here. It looks like for visualization number 7, we're going to find some Z-scores. Future Brian's going to put the cuts in here. Let's go. Okay, I'm pulling up the class. Let's hop over to the main. And let's go take a look at finding a Z-score. It might. Let me double check. I don't think I mentioned that in the video last time at least. So it's asking for the 4 parts of a confidence. Oh, yeah, the 4 parts? Okay, yeah. So the 4 parts are not going to be the Z-score. Good question right there. The 4 parts of the confidence interval are going to be, boom, right here. So here's the 4 parts of the confidence interval. Let's mark them. Part number 1, part number 2, part number 3, and part number 4. We'll mark them in yellow right here. Here's the 4 parts for a confidence interval right here. And this confidence interval we were doing was talking about the mean hours per work that a student works. Yeah, no, Mary, good questions. Yeah. This is what office hours are for. Like, you know, can you explain, you know, what the 4 parts of the confidence interval are? It's just the 4 blanks that we would fill in. So I don't always call it like the 4 parts. It might actually say that in the notes somewhere. But it's the 4 blanks that I put right here with the I am blank % confident that the true blank is contained in the interval blank to blank. And make sure this, usually there's a mistake here where this time we're doing quantitative. So if we're doing quantitative data, we want to make sure we say the true mean hours students work a week. So I am 94.5% confident, look where the highlighting is, that the true mean hours of work that students work a week, because that's what my interval was made to estimate, is contained in the interval 6.899, which is the lower, to 9.22, which is the upper. So that's the only part we need to say for the explanation. And you would do the same thing for this interval right here. I was showing how to do the conditions right there. Cool. So this interval right here was trying to estimate students in Greek life. So this interval right here is estimating students in Greek life. You're welcome. Yeah, no, these are great questions. Thank you for being here. I'm sure people are going to benefit from this part of the video on how to interpret confidence intervals. So yeah, of course, Megan, feel free to ask. Thank you for being here, Megan. I am 98.5% confident that the true proportion of students that are in Greek life. Now, Mary, why did I say proportion right here for I am 98.5? And here, let's highlight it. I'm going to do the color highlighting so we can see which things we're talking about. The confidence level is given right here. And the lower and the upper is right here. And we're talking about, oh, we should do context. Let's do a green for context. So that way we can see. I like that green better. Greek life is the context. So this portion right here is the context area. So I am 98.5% confident that the true, and then we have to do the context, proportion of students that are in Greek life is contained in the interval 31.9855 to 45.00728. Yeah, well, we just, no, don't worry, Megan, we just did that one, but let's do it again right here. It's a really good problem, but do not worry. Don't be like, Brian, so we just did it. No, let's do it. Let's do the human pregnancy one again. It's a pretty tricky one. It's a good starting out problem to understand. Let's go take a look at that problem. I'm gonna have to reset it to do it though, but do not worry. Let's hop back here. We're gonna put a cut in the video. I put these cuts so that later on when I mark the videos, so as many people know, you can come back and watch the videos later and they have cuts, but don't be like, oh, I shouldn't watch it now. Like if no one comes to office hours and no one asks questions, then I'm stuck here just talking to myself. And that's no fun. We don't get questions answered. We don't, then I have to make up questions. Let's hop over to the main screen. Okay, so we're back. This is a really great problem to understand the basics Just a really good problem to like know what's going on, because the first thing we see right here with this problem is that human pregnancies can be described by a what model? A normal model. So as soon as we see this, we need to think, hey, David M. Lane. We're going to go and talk to Mr. David M. Lane, and he's going to give us the normal model. The normal model is the Gaussian curve. It's the unimodal symmetric curve, and we've got it hiding down here. The website that just appeared on the screen is this website. And so with this normal curve, we can then show what human pregnancies would be expected to look like. We're going to take right here the mean and the standard deviation, a mean of 263. We're just going to put it right there, and a standard deviation of 14. And we're just going to go ahead and put it into both applets. Now, the difference between these applets is as follows. This first one right here allows you to put in numbers like what is the probability that a single woman would have a pregnancy that lasts more than 280 days? And that's the probability right here. Now, if you put above 263, you'd see half of pregnancies are expected to last longer than 263 because that's the mean. And it gives you the probability down here. Above 280, we'd expect about 11.23% of women to have pregnancies that last more than 280 days. And you can do below, between, all different values right here to figure out at certain points. This one right here allows us to put in percentages to say how long are the longest 5% of pregnancies. So the longest 5% of pregnancies are 286 days or longer. That's the longest 5% of pregnancies. So when we look at these problems, it says what percent of pregnancies would last between 265 and 275. We just go here to the first one and we say between 265 and 275, not 175. And there it is. And if you look, we won't cheat yet. This is between 0 and 1. Using the empirical rule, I know that this has to be less than 34. So this is actually a decent test question. A lot of people say, well, how would you ask this on the test? On the test, we could give you multiple choice where maybe we give you 40%, 25%. We just give you two choices. It's going to be 40% and 27%. I should have went with 25. 25 was so close. Oh, I could have probably guessed 25. How do I know this? Because in between here and here is 68. Half of 68 is 34. So I knew it had to be less than 34. You're not meant to estimate it that precisely a lot of times, but having a decent understanding of how the empirical rule works is going to help us out with guesstimating these answers and understanding for the test with the empirical rule. At least, and we can use David M. Lane to solve right now, but we should have an understanding of the 68, 95, 99.7. You carry that with you in your head. So when you look at that, you say, oh, that's less than 34%. At least how long should the longest 30% of pregnancies be? And so when we look at the longest 30% of pregnancies, that's going to be about there, which is going to be about 271. And we need to go to the other side of this where we go here, and it's 270. Pretty close. It's at about here-ish. And so 270.342. Now, this question right here is a review of Chapter 5. We should know these things, but this is a review of Chapter 5 so far. So everything right here has been a review of Chapter 5. But down here, we get into Chapter 14, where we're doing the distribution of the sample mean. So what am I trying to say? Well, Chapter 5 is about single observations, and the distribution could be skewed. But Chapter 14 down here is when you do the distribution of the sample mean of sample size 10, 25, 100. Yeah. We'll do that next, Madison. You got it. So what do we notice? The distribution of the sample mean will always be water to the distribution of the mean. And look at this portion right here. The distribution of the sample mean will always be water, because look at what's happening to it. And look at the equation right here. What will change about the distribution of the sample mean? It'll be more normal, which is good because we want to use the normal model. So it'll be more normal, and it'll be what? And this is two parts of the central limit theorem. Part number one, it'll be more normal than the original distribution, which is up here for single observations. But the distribution of the sample mean, which means we're taking observations and averaging them together to get a mean of sample size, let's say 100, will be more normal. And then one other thing we should know instantaneously, and it's there in the equation because we're taking the original standard deviation, dividing it by something. Standard deviation is variability, so the variability will be water. The variability is going to do what? You can see it here visually as we look at this. As we increase the sample size, it'll be more normal, and it'll also be water. What also? So central limit theorem states that as the sample size increases, the distribution of the mean will be more normal and tighter. So we have the formula right here that we need to use. This top formula states that the mean will stay the mean. So the mean right here of 10, if this is the mean right here of this distribution, it will not change. This still has the same mean no matter what. The mean will stay the mean. So that actually answers our question right here. We know the mean. The mean is 263. So for a sample of 90 women, the mean would still be 263. But the standard deviation is going to change. We're going to use that formula we just saw where we take the original standard deviation, sigma, and divide it by the square root of n. So the original standard deviation was, let's just go right here and draw it. The original standard deviation in the problem given was 14, and the sample size was 90. So the original standard deviation was 14, 90 square root, 14 divided by that, and there's the new standard deviation. So the new standard deviation is just the original standard deviation, 14, divided by the sample size of 90. And there's that. What is the probability that we have pregnancies for these 90 women? On average, the mean of it, because we're not doing single observations now, the mean for 40 women being less than 261. And we got to be careful if it says less than or greater than. I've definitely made mistakes on that. So we're going to go back to Mr. David M. Lane, and we're going to put in that standard deviation. You should be fine if you annotate the decimals or not, but we want to look here less than below 261, which is going to be, it's going to be in here somewhere. So it's going to be about, if it's right, no, it's about more like here. So about 10%. 261, right? About 10%. 8.77%. So we got kind of close. Kind of close. That should be right. 3 decimals, rounds up, close to 10%. 10% was a good guess. There we go. Is that making sense right there, Megan? Does this problem make more sense? This bottom portion is the distribution of the mean. The top portion is distribution of single observations. So at the top, you're dealing just with the usual single observations, and in the bottom, you do the new distribution of the sample mean of sample size 90. Awesome. Great job, Megan. Thank you so much. Great questions right there. We're going to put a cut in the video here. Everyone's like, we get it, Brown. We get why you go here. We get why you go to space to just chill out. You're welcome, Megan. Thank you so much for the questions. Really good practice, and hopefully understand the concepts, because that's the goal. Like, not just solve the problem, but understand the concepts, background breaks. Let's see. I think it was... Oh, yeah, we had about the conditions, right? Yes, let's go over the conditions here. Let's hop over. I'll bring it up so we can see it. Here we are. Let me go back in time, bring back my condition. Okay. Let's do this. See you in class, Adam. Good to have you here. Okay, so when we do the conditions, we have to remember the way to remember the conditions. I mean, that's a good thing to remember. We have here condition number 1. Oh, we got to do it. Everyone knows what's going to happen now. Let's hop over to lecture screen. So condition 1, you know it. Everyone knows it. Condition 1 is random. Random means we randomly select our data. So we need to randomly select our observations. So probably via doing your random selection and jump, you're probably okay. Condition 2 is less than 10% of the population is sampled. I usually call that just 10%. So whenever I'm drilling students on this, I say random, or I say, what's condition 1? Random. What's condition 2? 10%. Less than 10% of the population is selected. Now so I'm dropping some pretty big hints right here. I don't give the answer away on the other screen, but we're assuming that the population size is 4,000 something, like 4,122, and we're sampling 300 something. So think about how, remember, you're sampling 300 of 4,000. So, I mean, no matter what I'm just saying, is that less than 10%? Just look at the numbers and be like, we're sampling 300 something of a 4,000 population. Do we meet this condition? I'll let you decide that and think about the numeric justification to talk about, have we sampled less than 10% of the population? Now, we always pause here. We pause with a New York accent. We pause. Someone will be like, you're making fun of New Yorkers? Brian will be like, I am from New York. They're like, what? Well, yeah. So we pause and we ask ourselves, what kind of data are we dealing with? If we're dealing with categorical data, we'll be doing the success failure condition to some degree, like p hat or np hat and q hat greater than or equal to 10, np naught and q naught greater than or equal to 10, np and q greater than or equal to 10. If we're doing categorical data, which means we have questions like, were you born in Tennessee? Do you have a scholarship? Do you live on campus? These are all categorical questions, like yes, no questions. If we have a quantitative question, like how old are you, how much do you weigh, how tall are you, how much is your GPA? It's weird to say how much is your GPA, but like how much value of GPA do you have? Statisticians talk weird. That would make the condition the nearly normal large enough n condition, which deals with the central limit theorem, which we have the conditions for right here. Dealing with the shape of the distribution is the most important thing right here. We have to look at the shape of the distribution and ask, is it normal? Is it skewed? Is it heavily skewed? And then dependent on the shape, we need a large enough sample size, large enough n, to make it nearly normal. How would we say we sampled randomly jump? You would say it's satisfied by taking a random sample. Great question right there. And if we have two variables, this goes into later in the course, but if we have two variables, we might be doing a two-sample t-test, or we'd be doing a chi-squared test of independence, and that's why I have these colored right here. So if you're watching this portion of the video, these are all the conditions for the remainder of the semester and my step-by-step guide for what you do. Like pause here, ask yourself what kind of data you're dealing with, pause here before doing a fourth condition, and do we have two variables? Try to set your mind like this to be like random, 10%, pause, what kind of data am I dealing with? This would be chi-squared, two categorical variables. So if you have two categorical variables, expected cell count, and then you'd be doing count data. So that's why I have these colored this way. So I'll back here to the main screen. And I might see a lot of projects looking like this. And I'm the one who checks for plagiarism. So the good news is I can then be like, nah, it's not plagiarism. It's what I wrote on the thing. So you can basically say it's random because we took a random sample. That's what Jump did. So we are taking a random sample right here. So random sample. Less than 10%, we need to ask ourselves if our sample size of 321 here is less than 10%. And then when we're dealing with categorical questions, which the question I asked here is someone in Greek life? We have to ask, do we have at least 10 successes and at least 10 failures? And this would be met right here via NP hat and NQ hat greater than or equal to 10. So both NP hat and Q hat would be to be greater than or equal to 10. So as long as we have at least 10 successes and at least 10 failures, and just think about where that would be in this output, where the at least 10 successes, at least 10 failures would be in the output, not that bottom portion. Just trying to say right there. I'm going to reinstall some Microsoft Word. And then when we get down here to this one, where's the other output for it? I deleted that output. Sure, let's time travel. There we go. Do I have the conditions still on here? I do. I know all the time travel abilities, but I'm about to alter the timeline here. So this distribution right here is heavily skewed. So we have the same first two conditions, same. Now when we look at this, if you look at this right here, this is heavily skewed, but Madison, will I meet the nearly normal large enough n condition? And I want you to look at this right here. Do I meet the nearly normal large enough n condition? And how would you explain this to me right here with this? Looking at this distribution, which is heavily skewed, do I meet, because it's quantitative, we're asking how many hours a week do people work, and we're doing the mean for this. Do I meet the condition? And don't worry if you're wrong here, and then try to explain it. Just look at, here are the notes we have, here's the sample size, here's the shape of the distribution, and do we meet, that's not the right notes. Do we meet the nearly normal large enough n condition right here? Do we meet the nearly normal? So do the first step, then do the second step, and then look at the third right here. Do we meet the condition? Do we have a sample size that is large enough such that the distribution of the mean is nearly normal? Do we have a sample size with our example right here? This is heavily skewed. Here's our sample size. Do we meet the third condition? How would you describe that? And then I'll describe in words. And then we've got the conditions right here. We're doing large enough n because it's quantitative. Would we meet it? Yes. Since the distribution is heavily skewed, we need a sample size of at least 100. Our sample size is 321. Oh, Andrew, you're not old, man. I got called old one time when I was like 26, and I was like, psh. I thought it was weird then, and now I'm almost 40. I don't even feel old now, except when I feel old. Because, and then I would quote that number. I would quote that number right there. That's the important number to quote. Like, you need to quote the shape of the distribution and Yep, the 321 is larger than, so that is a large enough n such that the distribution of the mean will be nearly normal. Because what we're dealing with, traveling back forward in time, we didn't destroy the timeline completely. Look at that. Timeline intact. We didn't destroy the timeline. Thanos did not make us go away right here. We're going to have some fun day. So the distribution of the sample mean will be this. It'll be more normal and tighter. And I'm probably going to... Does that make sense, Madison? The distribution of the sample mean the distribution of the sample mean is right here. I think that's got it. I'm gonna go run to my office real quick. Andrew, hang out here. I'm gonna go run to my office, sit down at my desk for a moment, grab some food. So everybody, hang out for a moment.
Hey Brian, what's up?
Hey Adam.
Oh, what's this?
Adam, what are you doing? Adam.
No!